Okay, so now discuss what are called Legendre transforms and their connections to symplectic structures on the Lagrangian side. Okay, and I'm going to do this both in the continuous and discrete cases. So there's continuous and discrete Legendre transforms. And symplectic forms. Okay. All right. On the continuous side, Lagrangian and Hamiltonian mechanics are related by this Legendre transform. So Lagrangian and Hamiltonian mechanics are related by the Legendre transform. Okay, and so it's denoted by this blackboard bold F and then L, and it's a map from the tangent bundle of the configuration manifold to the cotangent bundle of the configuration manifold, and it's given by the following, right? So if you take FL and you apply it to Q and Q dot, right, you get Q comma DL dQ dot evaluated to Q dot. Okay. All right. So this is the usual continuous Legendre transform. Okay, and it relates the flows of the Lagrange equations with the flows of Hamilton's equations. And usually there is an assumption, it's like that this Legendre transform is invertible, and if it's globally invertible, we say that the Lagrangian is hyperregular, and then if it is not invertible, we say that the Lagrangian is degenerate. Okay. All right. So let me just sort of briefly remark that this Legendre transform is an example of what is called a fiber derivative. Okay, and it's called a fiber derivative because it is related to a fiber bundle picture. It's like of the tangent and cotangent bundles. Okay, so if you have a tangent bundle, and you can think of a projection over the base point Q, and what it does, of course, is to take Q dot and map it to just Q. Okay, so and then a fiber of this bundle is really just the preimage of one of the points. Okay, so in this case, it's really, if you will, this is really just TQ of Q, right? So if you have a tangent bundle, it's like then the fiber, it's like over Q is really just the tangent space at Q to the manifold Q. All right, but one way to sort of think about this then is that if you have a base point Q, then the fiber variable is really the velocity variable here. Okay, and so that motivates this idea of referring to the Legendre transform as a fiber derivative because you're differentiating the Lagrangian, right? So the fiber derivative of the Lagrangian, you differentiate the Lagrangian in respect to the fiber variable. Okay, because you are differentiating the Lagrangian, which is defined, it's like on a fiber bundle, right, with respect to the fiber variable, which in this case is just Q dot, okay, in that case, right? All right, so the reason why I bring this up is because this is going to naturally motivate what the discrete analog Legendre transform will be in the discrete setting. Okay, so so here we viewed the tangent bundle, it's like as a fiber bundle over Q. You could imagine doing the same thing for T star Q, and as you might expect, T star Q, which has coordinates, positions, and momentum, will project down to just the position variables, and then the fiber variables are the momentum variables. Okay, so in fact, if you had a Hamiltonian instead of a Lagrangian, right, you have a Hamiltonian which is defined on T star Q, then you can talk about a fiber derivative of the Hamiltonian, which involves taking the partial derivative of the Hamiltonian with respect to the momentum variable, right? So that's, in fact, that's going to be the inverse map. It's like associated with the Legendre transform defined in terms of the Lagrangian. Okay. All right. Anyhow, so let's look now at the discrete case then. Okay. So so similarly, right? You can view Q cross Q as a fiber bundle over Q. All right, but now you have a choice, because there are two ways it's like to do the projection, because you can either view the first slot or the second slot as the base variable. So you could have Q cross Q projected onto Q, and you could have, say, pi plus, which would take Q0, Q1 and give me Q1. You could have a pi minus, which takes Q0, Q1 and gives me Q0, right? So there's sort of two ways now of defining these projections. It's like, and as a consequence, there are two things which you can think of as being fiber variables. So both the things in the first or the second slot can be a fiber variable, depending on how you interpret this as a fiber bundle over Q. Okay, anyhow, so this, in any case, this leads to the idea of discrete Legendre transforms, right? So this leads to discrete Legendre transforms. Okay, so all right. So again, it's like you start off with a Lagrangian, which depends on, you know, position and velocities. You differentiate as for the fiber variable to give you a fiber derivative. All right. So now in the discrete case, right? So in the discrete setting, right? What you have is that you have LD, which is a map from Q cross Q to the rails. All right, and we want to look at now the two Legendre transforms, two discrete Legendre transforms associated with this. And again, it depends on which copy of Q you think of as the base point, and its sort of, you know, as a consequence of that, which of the copies of Q you think of as the fiber variable. Okay. So in the discrete setting, you have LD, then the discrete Legendre transforms. All right, given by. So I'm going to write this as F plus LD, right? And what it does is that it takes Q0, Q1, and it gives you something where Q1 is the base point, right? So Q1 is the base point. And then you have D2 LD Q0 Q1. All right. And then there's F minus LD Q0 Q1. And then this has Q0 and then minus D1 LD Q0 Q1. Okay, all right, so again, now you have two discrete Legendre transforms, okay, in contrast to the one which you have in the continuous case. All right, so I did want to say it's like how, you know, this is related to symplectic forms. And so let's see how all this is related. Okay, so I'm going to erase, it's like the board, but I'm going to copy this definition of the continuous Legendre transform down here. And let's just see what happens. Okay. All right. All right, so we have the continuous Legendre transform, right? So that's FL, which maps Q and Q dot to Q and DL, the Q dot. Okay, all right, so we have the canonical symplectic form, right? Okay, on T star Q. All right, and then we have these maps. All right, so let me draw a picture here. Right, we have T star Q here. We have TQ. We have a Legendre transform, which I denoted by FL. Right, and then there's another map from Q cross Q to again T star Q. I should have said that these are in T star Q. Right, which are now F plus minus LD. Right, the discrete Legendre transforms. And then on here I have a canonical symplectic structure. And I claim that with these maps and that canonical symplectic structure, I can define symplectic structures on TQ and Q cross Q. As you probably know, it's like these are sort of the obvious things you'd get by pullbacks. Okay. All right, so I'm going to write omega LD here. And you might think, well, you know, there are two discrete Legendre transforms. I'm pulling back omega. Why don't I get two discrete symplectic forms here? And it turns out that they're going to agree with each other. So I'm just going to omit the plus minus on that. Okay, so the continuous Legendre transform L, right, induces omega L, right, which is of course nothing more than the pullback of the canonical symplectic form by the Legendre transform. So this is the obvious thing. Okay, and you can write down what that is in coordinates. Okay, so in coordinates this looks like d squared L d qi d q j dot d qi wedge d q j, all right, plus d squared L d qi dot d q j dot, and then d qi dot wedge d q j. Okay, and then where omega is this canonical symplectic form of T star Q. And there is similarly a discrete symplectic form. It's like on Q cross Q, which is induced by the discrete Legendre transforms, right? So the discrete Legendre transforms F plus minus LD induce the same symplectic structure on Q cross Q, which I denote by omega LD, and it's going to be equal to F plus minus LD. So it's insensitive to which one of them you pick. It ends up giving you the same answer. Okay, and it is given by d squared LD Q0 I Q1 J dq0I wedge dq1j. Okay, and this is independent of which discrete Legendre transform you picked, right? Was used. Okay, so they both give you the same discrete symplectic form. Okay, and then, all right, so I should say that the Euler-Lagrange flows then preserve this continuous sort of Lagrangian symplectic form, omega L, and then the discrete Euler-Lagrange equations preserve the the discrete symplectic form omega LD, right? So just sort of state that, right? So Euler-Lagrange flow preserves omega L, and then the discrete Euler-Lagrange flow preserves omega LD. Okay, and of course it's like I guess I should also say that the Hamiltonian flow preserves omega. All right. So, all right. So those are sort of this equivalent notions of symplecticity. At least when the Legendre transforms are invertible, right? Then you can write the dynamics. It's like in these three different spaces, and they all end up being related to each other, and they all have symplectic structures which are related by the obvious way with respect to pullback. Okay, so let me stop here for now.